Hello! Let's use some Python to solve some discrete math problems. So, if you aren't in discrete math, I'm not going to explain combinatorics to you, but at least we can write some code to solve our combinatorics problems for us. So you'll still have to do the figuring out of what structure things are, but I'll show you how we can program basically for these formulas. Ignore that bottom one, it's wrong. Um, and put these into a Python program so that you can have something to calculate your permutations and sets and all of that, all in one place. So I'm going to need to import the math library, and we're going to need to define the permutation function and the combination function first. But then we can have a little program that asks the user what's your in value, what's your r value, and then solve it for us. So for a permutation, we need some in and r value. In is like all of the options, and r is what you're selecting. And then what we're going to do is, I like to calculate my numerator and denominator separate, and then return numerator divided by denominator. Because again, this is our permutation formula right here. So what it's going to be is numerator is math.factorial of n. Denominator is math.factorial of n minus r. And now we can calculate a permutation. So for instance, discrete math combinatorics, yay! N equals input. Enter your n value. R is input. Enter your r value. Then we can figure out what the result is. So permutation is p passing in n and r. Print out result. Permutation, or let's put permutation is this. So if I run this, if we have 5 items and select 5 items, oh, why do I always forget this? What is it doing? Oh, this is a string. Oh, Python. Gotta make this harder than it has to be. Okay, 5 select 5. So we have 120. So really quick, if we were looking at just how a permutation works, 1, 2, 3, 4, 5 spots to choose from, and we have 5 options. So let's say we have A, B, C, D, E. We don't really care what the values are. But for the first item, we have 5 places to put it. Oop. Want to keep this in the dock. Oh, that's not working. Good. Well, this is fun. So for our first item, we have 5 options of where to put things. Here we have 5 places. So let's say A is just going to go here. So second time, 1, 2, 3, 4, but this place is taken. So second item, we have 4 options of where to place it. So let's say B is going to go over here. I'm not going to write it there. I'm going to write this again. 1, 2, 3, 4, 5. A is here. B is here. Third item, we have 3 options left. Number 4, 1, 2, 3, 4, 5. Sorry, it's not the most attractive looking drawing, but let's put C there. So our fourth item, we have 2 options remaining. We could go here or here. 5, 1, 2, 3, 4, 5, A, B, C. Let's put D over here. Our fifth option, or fifth item for E, we only have 1 option left. We only have 1 place we can put that. So when we end up, we can have D, B, C, E, A. So basically you could organize these in all sorts of orders. What does this mean? Well, to figure out all of the different possible ways you could fill out 5 letters in 5 spaces, or 5 somethings in selecting 5 from 5, we'll have 5 options and 4 options and 3 options and 2 options and 1 option. So 5 and 4 and 3 and 2 and 1, or 5 times 4 times 3 times 2 times 1. So you'll at some point cover the product rule, and that's a long way you could do this. But if you can identify that this is a permutation, you could also just put P5 select 5. That will give us n over n minus r. N minus r down here, that's going to be 0 factorial, which is just 1, which gives us 5 factorial, which is 5 times 4 times 3 times 2 times 1. This is 20. This is 6. This is going to be 120. So then that's to double check this work. That's if we had 5 select 5. We can also test this out. Let's say we have 3 options and we're selecting 2, so then we get 6. And I could write this out as well if that helps. Let's say we have A, B, and C, and we only need 2. Well, here we have 2 options, but we have 3 things to choose from. So let's say we have A, 1, 2. Now we have A, B. So it could be A, B. We could come up with B, A. We could have A, C, C, A, B, C, C, B. So, like, we have 6 different ways we can organize 2 things given 3 choices to choose from. Okay, so that's the permutation. If we want to calculate for sets, so let me just put this here. Permutation, order matters and no repeats. If we have a set, order doesn't matter, but still no repeats. So in that case, we're just going to implement this version, this formula here. Define C, N, and R. Numerator is going to be mostly the same, except we have to add math.factorial r times the n minus r. So set, I can't use that word. My set is C, N, comma, R. Print combination. And a combination. Oh, no, not combination. Sorry. I'm mislabeling these. This is a set. You use the combination function for multiple different, like for the unordered list as well. So we run that. Let's say 5 select 5. Well, we have one way we can select 5. The reason for this is because with the combination, order doesn't matter. So you'll often see these as like, we have 5 people to choose from, and we need a committee of 3 people. So you'll see 2 versions of this. You'll see one where it's committee of 3 people, and you'll see one where it's pres, vice pres, and secretary. This version is a set. This version is a permutation. So for this version, it doesn't matter if we have Bob, Alice, and Jane, or if we have Jane, Bob, Alice. In this case, as a committee, this is considered the same committee, no matter which order you list them in. But if this were ordered, you'd think of this as the president is here, the vice president is here, and the secretary is here. So then, depending on which order these were in, these would have different significances. This would mean different things for a permutation. But we're not talking about a permutation here. We're talking about just a committee. So let's say we have person A, B, C, D, and E. So 1, 2, 3. We have three places, but again, remember A, B, and C is considered the same as C, B, and A. With the set, a set like this, A, B, C, order doesn't matter. So these are considered equivalent. So that's why we end up with only, if we have 5 people and we're selecting 5 people, it doesn't matter what order they're in, there's only one option. So if we had 1, 2, 3, 4, 5, A, B, C, D, E, we're using all 5 people. That really just gives us one option, whether it's in this order or a different order. But let's say we have 5 people, select 3. There are 10 different ways we could do that. So we would have to think, if we wanted to list everything out, we could have ABC, ABD, ABE, ACD, ACE, so on and so forth. So there's a lot of different ways, but order doesn't matter. So we have calculated a set here. Now let's look at ordered list. Order matters. Repeats allowed. So in this case, this would be like if one person could fill multiple roles. So you don't usually see something like a committee question or something like that with a ordered list. Let me just scroll down in my document. This is old discrete math stuff that I wrote for my students. That's sets. Let's look at ordered list. This is unordered list. Where's ordered list? Did I put them? Did I not? Okay, there we go. I guess I put them first because they're the easiest to calculate. So if you have something like you are rolling 2 dice, red and green, how many results are possible? Well, you'll see dice problems with ordered lists, but not like people problems, because you wouldn't have Bob be every roll in the committee. But if you're rolling dice, you might get 2 multiple times or 3 multiple times. So in this case, we're going to need to do, let's say, order. Well, I mean, we don't have to. We can just do the math here. Ordered list is going to be math.power into the R. So there are into the R ways of choosing. Ordered list. So for example, we are rolling 2 dice, a red die and a green die. How many results are possible? Well, for 1 die, there is 6 options, and we are going to roll 2 dice. So the result is going to be 36 different ways. Or if we thought about flipping a coin, each coin has 2 values. Let's say we're flipping 3 coins. Oh, it didn't like that. Oh, because of this part. Well, maybe I'll have to ask the user which one they want to compute. But if we had, where is my drawing program? It is down here. If we have a coin, well, a coin has 2 sides. And if we flip, 1 coin, how many results are there? We have heads or tails. We have 2 results. 2 coins, we have heads, 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 tails, tails, heads, and tails, tails. So we have 4 results. 3 coins, we're going to have heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails. This is like writing out a truth table, if you've done that before. I'm basically just using that same technique. There are 8 options. So we have 2 sides, 3 coins, that gives us 8. That's our n to the r, which isn't going to work for this permutation. So let's go ahead and add a question of type. So input, what kind of structure? And let's do permutation set ordered list or unordered list. Okay, and do if type is P, then we'll do this stuff. Else if type is S for set, we'll do this. If type is ordered list, we'll do this. And else if type is unordered list, we're gonna do some other things, but I'll copy paste this for now. Say unordered list, order doesn't matter, and repeats are allowed. So we'll just keep using this variable, and we need to adjust the math. So we're not going to use math.power for the unordered list. We are going to use something else. So let's look at some example problem, and I want to make sure I have the right formula in here. Let me just double check my math calculator. Well, that one, we'll look at that later. So for an unordered list, a lot of the times you'll see problems of building binary strings this way, where given r amount of ones and n minus r amount of zeros, there are c of n r ways to choose, so we're reusing the combination formula. So let's say we could ask them if they're doing a binary string, or we could ask them for the n and r value, but then they'd have to pre-compute that. But let's look at this. So let's say we're building a binary string of size 4, and we're going to have, let's say 1, 1. So for a binary string size 4, we could have 1, 0, 0, 0. Maybe I should do size 3. That'll be easier. 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. So we can put the 1 in any of these positions. We're going to have r amount of 1s, so there's going to be 1, 1. N minus r amount of zeros, so we have 2 zeros. And then we can solve for n. So n minus 1 equals 2. Do some little algebra here. N equals 3. So then to solve this, we would do 3, comma 2. So let's make sure this comes out right. We'll do c n comma r. Boop. And so we're going to use a unordered list. 3 comma 2 gives us the result of 3. And I wrote down all of the possible strings with this criteria so far. So that's, you would have to pre-plan that, or we could ask the user, let's see, how many ones? And we could say how many zeros, how many zeros. So we could expand this. Let's say binary string, so B for binary string. Elif type is B. We're just going to ask these questions and then readjust our math. So we have, where did I put that document? R amount of ones, n minus r amount of zeros. So r is going to be how many ones. N is going to be, and let me just rewrite this again. So we have n minus r amount of zeros. So we're going to need to solve for n. So let's say z is for how many zeros. N is going to be the amount of zeros plus the amount of ones. So how many zeros plus r. Then we can do our unordered list is c of nr. And unordered list, binary string. So we can test this out again. play. We'll say this is a binary string. How many, oh, oop. Did I not do that right? I wanted to ask how many ones. Why did it give me the wrong thing? Enter your n value. That's not what I want. B. No. Type is B. Oh, it asks us beforehand. Oops. We'll move this to just ask whenever it applies to what we're doing. B. How many ones? Well, we're going to have one amount of ones and two amount of zeros. And I forgot to wrap it as an int again because things. Gonna play. B. How many ones? One amount of ones. I typoed. This is why I prefer C++. Well, whatever. One amount of ones, two amount of zeros. We have three possible ways we can build this binary string. Alright. So that's solving these. I do want to show another type of problem, and I don't know how common they are. I know they're in the discrete math book that I solve with. So what we're going to do is another project. We're going to solve the Fruitbox problem. And then once all this is done, let's just make a special folder for discrete math. So it's all in one spot. We're going to do the Fruitbox problem. So what is the Fruitbox problem? I find that it's kind of a tricky problem for students. So what the idea is, this is using unordered lists. So with the Fruitbox problem, we have a box of fruit. Let's just say it's a very long box, and we don't want these fruits touching each other. So we have like an apple here, and then we'll have a separator, we'll have a banana, and we'll have a separator, and then we'll have oranges, and maybe that's all we have, 3 different types of fruits. And the question is, how do we figure out how many different ways we can stock this box with fruits, including if we have 0 apples or 0 oranges or 0 bananas. But it usually shows how to solve this with a binary sequence. So we'd have 0, 0, separators would be 1, 0, 0, 0, separators would be 1 again. So this is one example of a binary string with 1, 2, 3, 4, 5, 6, 7, 8 total fruit items with 3 fruit types, meaning we have 2 separators, and just it kind of gets muddled in all of the examples. I haven't found a really good way to that is like very clear in a book or an example. So what I'm going to do is I'm going to write a Fruitbox solver so I can actually show you how this is solved. So with a Fruitbox problem, let's define our combination, because we need that function for solving this for any unordered lists. We are going to ask the user how many different types of fruit there is. So input, how many types of fruits? Or to make it more clear, how many different types of fruits? This would be, if you have apple, banana, orange, you'd have 3 different types of fruits. So then the amount of separators in the box is going to be the amount of fruit types minus 1. We'll ask the user how many fruit total are we going to store? How many total fruits to store in box? And from there, we'll get the total box spaces or slots or, places for things in the box. It's going to be however many fruit we're carrying, plus the amount of separators between each fruit. So I usually like to think of this like a donut box or something like this. Let me open my discrete math notes again, wherever I have them somewhere. I like to draw them this way. You have these donuts and you have these little slides in here to keep them from touching. But each thing is a spot. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces in the box. And those separators are going to take up space, whether they're at the very end, because maybe you only have one type of donut, but they're still there, they have to be there and take up space, or if they're separating 3 different types. So, total box spaces, and then we could figure out total ways to store our fruits or donuts plus the separators is going to be a combination. We have the total box spaces we're choosing, and then the fruit count, or this will give us the same thing, total ways, total box spaces, select the separators. So let's say total ways to get fruits will be total ways, and I'll print it out down here again. These will be the same value. So let's say we have a box. We have 3 different types of fruits. Dang it! I always forget this part. Don't have to do this in C++. Okay, 3 types of fruits. We're going to store 10 fruits in the box, so that means there's going to be 12 spaces in the box, 2 separators and 10 fruits. Oh, it didn't like something. Oh, I didn't import the math library. Import math. Okay, let's try this again. 3 fruits, 10 fruit, 3 types of fruits, 10 fruits in the box. 12 total spaces, 2 separators. So there's 66 ways to order these fruits. Let's just go ahead and print out total separators. Let's just print out the stats first. Separators. Print fruit types. Fruit types. And I'm going to put like a nice long separator here just to keep the program looking nice. Total fruits. Fruit count. Print total box spaces. Total box spaces. Oops. Spaces. Yeah. And I'm gonna just put some spaces in here to make that look nice as well. We'll run this again. How many different types of fruits? Let's have 5 types of fruits, and we're storing 10 in the box. So we have 5 types of fruits, 4 separators, 10 total fruits, and 14 spaces in the box, because we have the fruits plus the separators. So then we'd have 1001 ways to store all of that. Okay, let's try it again with something smaller. Let's say we have 2 types of fruits and we have 4 spaces in the box. And we'll just try to draw this out. So we have 2 types and 4 spaces. So then we at least need 1 separator. I mean, we are going to have 1 separator, not at least. So let's look at this. We'll have, I'm going to just draw these as shapes, but we'll have, let's say we have 1, 2, 3, 4, and we have separator at the, or 3, and the separator at the end. Is that how I type this out? 4 total fruits. Oh, there has to be 5 spaces. Okay. And the 1 separator. So this is one of the boxes. This has none of the, let's say, square fruit. It all has triangle fruit. We could also have all square fruit as well. And let's say normally there'd be a separator between triangle and then square. So that's one option here, one option here. We should have 5 total ways. So we can also have triangle, 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 separator, square. So that's still 4 total fruits. This is 4 fruits and 5 spaces. Okay, we could have triangle, triangle, separator, square, square. And we can have triangle, separator, square, square, square. Okay? Or if I put these in like a nicer order, this would be at like the very bottom as a different option. So move these down here, kind of tidy these up. We could have 4 triangles, 3 triangles, 2 triangles, 1 triangle, or 0 triangles. And these are all of the different ways, 5 ways to buy 4 of 2 different fruit types. Okay, so hopefully I think this makes it a lot more clear when you're looking at it in terms like having nice long variable names in coding rather than single letter variable names in math. And hopefully that illustrates for the unordered list type where we have a Fruitbox problem, we're selecting the total amount of box spaces, the fruits and the separators, and then either the fruit count or the separator count. So hopefully this kind of helps with a little bit of Python, maybe a little bit of discrete math. Um, I have my students write these operations right here for their stuff when I teach this class. And it can be helpful just to kind of look at things as if you were applying it in code. So hopefully that helps. Thanks for watching.